Maybe we can send the views on this thing off the charts virally. We're gonna talk about exponential functions here. Exponential functions are functions of this form down here. F of x is b to the x. Now, there is a little bit of a condition on f of x, and that is f of x, or the b in that thing, has to be a value greater than 0 and different than 1. So there's two functions here. One of them is 2 to the x. The other one is x to the second power. Which one of them, or both, or neither, is an exponential function? Is that the exponential function? Both of them are? Well, with the exponential function, you have to have a variable in the exponent. And here you got a fixed number in the exponent. This is what we're familiar with, right? That's just a parabola. But the other one puts the variable in the exponent. So that's going to make a big difference in terms of the behavior of this function. And let's see and appreciate that by actually plotting some points. So I've got a fairly general set of points here. And we'll plot each of these for f of x and g of x. Let's start with g of x because that's going to be the easy one. 0 squared is 0, 1 squared is 1, 2 squared is 4, 25, 100. Does anyone know what 20 squared is? Where's my mental calculators out there in the audience? 400. All right, well done. Let's see what happens, though, in contrast when we start looking at 2 to the x power. For instance, 2 to the 0. What's anything to the 0 power? 1. 2 to the first power is 2. 2 to the second power is 4. How about 2 to the fifth? Anyone got that one? 32. Well done. But here's something kind of surprising. 2 to the 10th power. It's really 32 squared. 1024. So at least for a little while, these two looked kind of comparable. I mean, you got 1 and 0, 2 and 1, 4 and 4, 32 and 25. They look pretty similar. But all of a sudden, 2 to the 10th power is 1024. If you square this, if you square 1024, you get 2 to the 20th power, which is a staggering 1,048,576. Wow. That one's going off the charts. So I've got two graphs on the little Cartesian coordinate system here below. I want you to take a minute and decide which one do you think is f of x and which one do you think is g of x. So which one is f of x, which one's g of x? So take a look at your x and y coordinates, because basically these are your xy pairs, 0 and 1, 1 and 2, 2 and 4, etc. Or 0, 0, 1, 1, etc. Which one's which? So which one's f and which one's g? How about this first one right here, the taller of the two? Which one is that? Is that f or is that g? F. Because the thing that you should be noticing is that this function is just skyrocketing. It's taking off. It's getting really big, really, really fast. I mean, take a look at a modest number like 10. 2 to the 10th power is 1024. That's way off the charts. Over here, 10 squared is 100. So we can do that one. That one fits here. But we don't have room for that for our exponential function. So this one's f of x. And the other one's g of x. Let's take a look at things on the other side of the x-axis. Values of x that are negative. So for values of x that are negative, Let's take a look at, well, 0 squared is still 0. Negative 1 squared, doesn't matter if we square 1 or negative 1. You're still going to get 1, 4, 9, and 16. Some familiar values there. 2 to the 0 we already did. But how about 2 to the negative first power? What does that equal? Yeah, it'd be 1 over 2. So 1 over 2. How about 2 to the negative second? It'd be 1 over 2 squared, but 2 squared is 4. So we get 1 over 4. And 2 to the negative third? Not quite. 2 times 2, 2. 1 over 2 cubed. Yeah, 2 cubed is 8. And the last one, 2 to the negative fourth, is 1 over 16. Yeah. So, wow. What's the pattern with these numbers? What are they all getting closer and closer to, but they'll never actually touch? 0. So you're getting close to, but never quite touching 0. So again, I've got 2 graphs drawn. Try and use your little t-tables here and decide which one do you think is f of x and which one do you think is g of x. So here's f and here's g. Try and figure those two out. And in so doing, we're getting acquainted with some of the features of the graph of an exponential function. Okay, so this one right here, that U shape, is that g of x or is that f of x? G of x. This is your parabola, right? That's what you expect from the graph of x squared, and it doesn't disappoint you. So we get something like this. Now for our other one, to the right of the y-axis, you see the function taking off. But to the left of it, you're getting closer and closer to the x-axis. Closer and closer to this line, y equals 0. And y equals 0 is going to have a special name for us, or that line here, because this is what's called a horizontal asymptote. So down here, some of the conclusions that you should be getting. The graph of the exponential gets close to the x-axis. See, isn't this cool? It's an interactive handout. Woohoo! Awesome. Yeah. Yeah. Brilliant. Extra credit over here for Luke. So y equals 0, but it never quite touches the x-axis. You'll never actually get to 0, but it gets really, really close. And that's called an asymptote. Be careful how you abbreviate that, please. Thank you. All right, come on. Good job. Good job. All right. A couple other conclusions that I want us to be observant about with respect to our exponential functions, and that is the first one that we saw is that these graphs grow really, really quickly. And I'll try and demonstrate that very dramatically in just a minute. But for x greater than 0, the graph grows very quickly. So that's one thing. The other thing that we're going to want to take note of is the y-intercept of this graph. How do you find the y-intercept of a graph? In any graph, not just this one, but any graph. What do you set to 0? Set x equal to 0. All right? Tell you what, let's do that right up here in this most general of exponential functions. X, y. If I set x to 0, then I'll get b to the 0 power. What's something to the 0 power? 1. So no matter what value of b you have here for your graph, this graph is always going to pass through 0, 1. And that's the point that I'm going to want to see graphed accurately on all your graphs, because we're going to start translating these graphs, shifting them left, right, up, and down. And when we do that, I want you to keep track of that point here. So this point here, 0, 1, your y-intercept, where does that get transferred? So passes through 0, 1. So there's three things that you should be aware of for the graph of an exponential. Now, I'll give you kind of a quick version of this. But on the board here, I'm going to draw a little graph of x to the second power. And I'm going to scale it in terms of centimeters. So here's 10 centimeters, 20, 30, 40, and 50. It's about as far as we really need to go. And then I'll scale it on the y-axis in the same way with 10, 10, 10, 10. And we're going to graph y equals 2 to the x. I just want to really impress upon you how fast this graph really grows. So let's do it this way. Starting with 2 to the 5th power. 2 to the 5th power is 32. So 32 centimeters, okay, that's going to be up here. And fortunately for me, that's the last point that I can graph. Let's see what happens. Now 2 to the 32 centimeters is about the height of a handsome athletic skier's elbow from the ground. Say about that much. All right. Now, what about 1,024 centimeters? That is 2 to the 10th power. How high would I have to go to graph this next point? Well, about to the top of the parking garage across the street. 1,024 centimeters, that's about 3 stories. Let's keep going. 2 to the 20th, 1,048,576 centimeters. How far? 10 kilometers. Yeah, 10 kilometers. A little bit more than that. So basically about 6.5 miles. So get on a good jet if you're going to graph this next point. So and remember, that's right here. That's at x equal 20. So at x equal 20, you're going to have to get on a nice high-flying jet. What if I wanted to go out to x equals, say, 35? So I'm right here. It's not very far away, but you'd have to go to the moon to graph this point. 239,000 miles away. And we'll do maybe 1 or 2 more here. 43 centimeters right here. I mean, easily within elbow distance, I'd have to go to the sun to graph that one. And if I want to go almost to the end of my arm, 61 centimeters, now I'd have to travel to the nearest star, Proxima Centauri, about 4.26 light years away. So, wow. I mean, that's ridiculous. Look at it. Just to plot that point right there within arm's reach, you'd have to go to the nearest star. What I'm saying is that exponential functions grow amazingly fast. And that's it's a fact that I don't want lost on you. Let's flip the sheet over and spend some time graphing these things. So I've given you 4 different versions of this graph. And the graph that's here is y equals 2 to the x power. This is great practice. This is exactly what I expect from you on the exam. So if you're not catching on to something, please ask some questions. So we've got this one, but what if I was to ask you to graph y equals 2 to the x plus 2? How do you think that that would affect my graph? I mean, all right, got to vote for shift to the left. Okay, that seems reasonable. Now, one way to kind of get at that would be to plot some points. I'm trying to think here. This point in particular is what I'm most interested in. that value right here. Where is that going to be on my new graph? Well, I get that point when x equals 0. 2 to the 0 is 1. So what would I have to put in to the exponent for x to get a 0? -2. So that point that was here is now over here. It's been shifted to the left by 2. Now, if you want to be really careful and draw a very, very nice graph, you can also do one more thing for yourself, and that is, let's graph the y-intercept. Now, I said that already today. How do you find the y-intercept? What are you going to do? Set x equal to 0. 0 plus 2 is 2. 2 squared is 4. So the y-intercept is going to be 4. And you can see that that's, again, been shifted over by 2. You got this point here, shifted over 2. You're going to get that. Now, the only point that I'm really concerned about is this one right here. That one I want to see drawn accurately. The rest of it is a bonus. But as best we can, we'll play connect the dots in a college-educated way. And I always kind of have to turn this around. Sorry if you're getting vertigo as I do this. Something like that is what you should get. Now, one thing you want to be careful of, remember you've got this line down here at y equals 0. The graph should come close to, but not touch, that line. Okay, good with that. Let's try another one. Let's try y equals x, or 2 to the x minus 2. What kind of a shift do you think this one's going to create? To the right by 2. So again, you can start out here and say, okay, well, shift to the right by 2. This is the point that I want to see off this graph. Make sure that one's drawn accurately. And then, as best you can, draw the new graph. Again, I'm going to have to pull this down. So, not my best, but tell you what, you don't laugh at mine, I won't laugh at yours. All right, fair deal there. So you got your horizontal shifts, and like our previous work with horizontal shifts, they always seem to go in kind of the opposite direction that you might think initially. The +2 isn't to the right 2, it's to the left 2. -2 is to the right instead of to the left. Okay, so no big shakes there. What if we were to graph y equals 2 to the x minus 4? How do you think this graph is going to be shifted? The minus 4 is not in the exponent. If it was in the exponent, you'd be exactly correct. It'd be shifted to the right by 4. How much? Yeah, this one's going down, right? All right, this one's going down by 4. But before we do that, let me remind you of an important feature of this graph. And that was this line, the horizontal asymptote. So we had a horizontal asymptote at y equals 0. Where's that horizontal asymptote going to be if I shift the graph down 4? At -4. Start out by drawing this at -4. In fact, if you want to borrow a ruler, I've got some rulers, or pull one out, etc. But let's draw our new horizontal asymptote. Now I'm going to draw it with a dashed line because it's not really part of the graph. It's just a feature. The graph gets close to it, but it never actually touches it. And we've got this on video now, which is cool. I will ask you for the horizontal asymptote on your graphs. So when you get tested on this, I'll say, hey, I want to see the horizontal asymptote. It's just shifted down however much this is, or up however much this is. Where's this point at 0, 1 going to be? If you shift it down 4, where's that new point going to be? At negative 3. You get shifted down 4. So 1, 2, 3, 4. Right here. And the rest of it is just to try and draw this curve. You know, just shift it down. I'm not going to be too fussy about, you know, how you do that. And again, let me pull this off to the side. You can graph some extra points for yourself. There's nothing wrong with that. You should get something that looks roughly like this. That's your new graph. Y equals 2 to the x minus 4. And again, you got to be careful that you notice that the minus 4 is not in the exponent. How are we looking on that one? Yeah, Demetrius? Good question. Because that 4 is not in the exponent. If it was in the exponent, if it was y equals 2 to the x minus 4, that's what would cause a shift to the right. But this one is 2 to the x, and then just subtract 4 from that. So, yeah, the answer is that it's not in the exponent. Let me give you one to try. And when you do it, I also want you to include the horizontal asymptote. Let's do y equals 2 to the x plus 3. And again, that plus 3 is not in the exponent. Yep. So you're going to have to draw a new asymptote, right? This one? So this graph is going to get shifted how? Up by 3. So start by drawing in your new horizontal asymptote. So that's going to be here at 3. Let's draw that in. I like drawing it in with a dashed line because it's, like I said, it's not really a feature of this graph. Or it's not a part of the graph, it's just sort of a feature that's a guide. The point here at 0, 1 is going to be up here at 0, 4. Again, you're shifting up by 3. Last but not least, I need to draw a nice increasing function like this to the right of my y-axis. If your graph accidentally touches this asymptote, I'm not going to worry. Where you're going to lose points is if it goes through it and keeps going, or if it ricochets and bounces off like a parabola. So both of those, we're going to get you more than a frowny face. All right. Looking okay with the vertical shifts?
These functions, will they pass the vertical and horizontal line test?
Yes. Yeah, that's a great question. They are one-to-one functions. So not only are they functions because they pass the vertical line test, but they're one-to-one functions, meaning they pass the horizontal line test. So kind of foreshadowing stuff in section 11.3, let's take a look at the graph of y equals 2 to the x. So that's something like this. In section 2.3, we're going to be graphing logarithmic functions and working with logarithmic functions. They're going to be the inverse of what these are. So x equals 2 raised to the y power. And now you're going to have something, instead of something that grows incredibly fast, you're going to have something that grows incredibly slow. So, yeah, nice observation. Both of these are one-to-one functions. So, great question. Back to this over here. Let's put two of these shifts together into the same problem. So, problem number 32. Y equals 2 raised to the x plus 1 minus 2. Well, there's a couple shifts going on here. Sarah, what do you see? What kind of shifts do you see taking place for problem 32 here? Good. Shift to the left by 1 and down by 2. Excellent. So the one point that I asked you to keep track of is this one right here. If that gets shifted to the left by 1 and down by 2, that new point should be down here at -1, -1. What else should I shift before I start drawing my graph? The asymptote. Perfect. So let's shift the horizontal asymptote. It was up here at 0. Now it's going to be shifted down to y equals -2. By the way, did I mention that I'm going to ask you to draw the horizontal asymptote on your test? All right. Yes, I did. Just another dig here to remind you that I do want to see that. That's y equals -2. My graph has to pass through this point and get close to, but never quite touch that. If you want your graph to be even a little bit more accurate, if you're looking at that going, oh, I'm just not really good at these things, you can plot more points. An easy point and a good point to get quite often is the Y-intercept. What would be the Y-intercept for this graph? How would I find it? Set x equals 0. Good. I hear kind of a theme here. So 2 to the 0 plus 1 is 2 to the first power. 2 to the first minus 2 is 0. So this graph actually goes through the origin. And, you know, some people seem to be averse to crossing this graph. If they're like, no, it's got to open wider. This one's actually going to cross the graph of 2 to the x here. And that's okay. There's no rule that says you can't cross them. So let's see what that graph's going to look like. And, well, I'll risk doing it this way. Something roughly like that. Okay. So two shifts. To the left by 1 and down by 2. Your turn for one is coming up. Before I give you your own example to work on, is there anything on this one that maybe I went over a little too fast, or just something in general that you're not quite comfortable with yet? Okay. Here's one for you to try then. Y equals 2 to the x minus 1 minus 4. So see if you can't graph that one. Include the horizontal asymptote. Okay, so a couple things in terms of shifts here. What's the x minus 1 going to do? Good. Shifted right by 1. And what else? Down by 4. All right, right by 1, down by 4. So, to the right 1 and down 4. 1, 2, 3, 4. That puts that point there. Let's also draw in our new horizontal asymptote. So right here at y equals negative 4. So I got those two. Y equals negative 4. And basically I just have to sketch this curve down here. If I want to help myself out, I can plot other points. There's nothing wrong with that. So for instance, at x equals 2, 2 minus 1 is 1. 2 to the first power is 2. 2 minus 4 is negative 2. So I get a point there. And if I went to the next one, at x equals 3, I'd end up at 0. So I can plot a few points and then draw my graph. So I'm going to take this one down for a second. So something like that. How are you feeling about these exponential curves? Feeling pretty comfortable graphing them? There's one last thing that I want to do in terms of a graph, and it's problem 34-ish. And I say ish because in problem 34, they're asking you to graph y equals negative 3 to the x. But since we've already got the graph of 2 to the x, let's deal with that. Let's just deal with negative 2 to the x. Now, yeah, it's a good question. What's going to happen to the graph instead of looking at 2 to the x if I look at negative 2 to the x? Yeah, it's going to flip it. So instead of opening up through the point 0, 1, where's your graph going to cross the y-axis? Any guesses? Yeah, 0, negative 1. 0, negative 1. Thank you. So that's going to be your graph. Let's put that one in pink here. Yeah, maybe I'll give myself one more point to shoot for. So something about like that. But it's just going to be a mirror image. This one's going to open down. Now you might keep in mind that the original question was negative 3 to the x. And you might say, well, wait a minute. What's the difference going to be there? How's that one going to look? And that's a good and fair question. Let me explain the effect of the base on the shape of the graph. Now overall, there was 3 things that I asked you to be aware of when you're looking at the graph of an exponential function. So let's shut that one off. Those 3 features were that the graph passes through 0, 1. That's one of them. It grows really, really quickly. And the other part is that it decays, it gets close to, but never quite touches the x-axis. So those are those 3 features. But what's going to happen if we look at it for a different base? Here it is for, let's see, there we go. Here it is for y equals 2.5 to the x power. And what's going to happen is I'm going to let this run, and it's going to change the value of the base, but the overall shape of the function is still going to be the same. So let's see that. So as it gets higher, the base gets higher, graph gets steeper, or as the base gets lower, it gets steeper, but it still always passes through 0, 1. It's still always getting close to the x-axis, and it's still, at some point, is going to grow exponentially. So, you know, if I do 2 to the x, 3 to the x, 4 to the x, you're still going to get that same pattern. In fact, just to maybe help drive that point home, let's just look at 2 to the x, and then y equals 3 to the x, and then y equals 4 to the x. Let's graph all three of those on the same plane. And you can kind of see what's happening here. They have the same general shape. So that's why we're just sticking with 2 to the x, because I already had it graphed for us. The big predominant feature about exponential functions is that they grow really, really quickly. And let's kind of continue with our slideshow here and see some more about exponential functions. Where in the world would you see an exponential function? Well, we saw one here. Those dominoes grew exponentially until it got down to that last one. And it's amazing that that little one started this whole chain reaction and knocked down this last one. That last one was a world record domino. It was over 30 feet high and it weighed a couple tons. And you set that in motion with a little tiny domino. So pretty amazing. The national debt. This is money that you guys owe. I'll be dead before they call it in. All right? This is what you guys owe. And by the way, your share as an individual is about $62,000 or so. Is how much you owe. I hope you enjoyed spending that, because that's about how much we all owe, really. The national debt, boy, that looks like exponential growth to me, right? It's taking off. Where else? World population. Get your lakefront property now. It's going to get tight, man. By the time you retire, this little Earth is going to have 10 billion plus people. That's a lot of people. A billion is a huge number. The other problem that you're going to face is carbon dioxide levels, global warming. Carbon dioxide levels are taking off compared to historic levels. We talked about this earlier. Gangnam Style was the first video to have 1 billion views. 1 billion. That's like almost 1 out of 6 people on this planet. It's huge. But when you talk about a video going viral, what does that mean to you, that a video goes viral?
Explodes up.
Yeah, it explodes up. And let me give that a mathematical context. A viral video is a video in which the number of views grows exponentially. And that's exactly what's happening here with Gangnam Style. The number of views just blows up, goes off, explodes exponentially. So that's what a viral video is in a math sense. Internet connectivity, devices that we have that connect to the internet, they're growing exponentially. An old one, I need to update the slide, but the fact is still true. Computer power. They get faster about every 9 months, called Moore's Law. The rate of computer processing speeds just keeps on getting bigger and bigger. And then on the flip side of things, you can have radioactive decay. We'll talk about that later on. But there's a ton of examples of exponential growth. This one's kind of a fun problem. We won't tackle it now, but the old problem of a poor slave does a favor for the king and asks for a reward. He says, tell you what, on day 1, I want 1 piece of rice on this corner of the chessboard. On day 2, 2, and then 4. And just keep going until to fill up the chessboard. And the results of this are pretty astounding, but maybe we'll save that one for later. For now, let's do 1 or 2 more problems to finish out this section. Let's see. What's that? Let's look at problem number 44. Problem 44 talks about the value of a computer X years after you buy it. So they tell us in problem 44 that the computer starts out at $5,000. Yeah. But that it's, what's going to happen after you buy something? Does the value increase or decrease? Decrease. So it's going to decrease according to this function. Notice that the base of our exponential function here is a number that's less than 1. So instead of exponential growth, you're going to get exponential decay. Let's figure out how much this computer is worth after 12 years. So it'll be f of 12. 5,000 times 0.75 to the 12th power. Hopefully, you can update your technology more than once every 12 years. I don't think I'd want to go back to the original iPhone right now. That would look really, really painful. But that's kind of roughly where you're at with this. So, take out your calculator, plug in some numbers, see what you get. It's not going to be much. Man, all the batteries on my calculator are really low. All right, there we go. Finally, third time's a charm. So 5,000 times 0.75 raised to the 12th power should be about $158. Yeah, $158. You able to get that number off your calculator? Yay. All right. Thank you. Thank you. You have to hit the caret, the up arrow, or the hat, the chapeau. One of those things, but it's the symbol above the division sign. So type in times 0.75, and then raised that character, and then it should allow you to type in the 12. All right. Did it? Really?
793, 651 over 5,011. Did you put 0.75 in parentheses?
Let me, the calculator's getting you your fraction. It could be one of your settings here. If you go to the mode, one of the things that it can do is give you fractions, I think, automatically. Let's take a look here. Let's see, normals, fraction type. Not real. In one of these settings, stat diagnostics off. Yeah, I'm not sure why it's giving you a fraction. It's one of these settings though. Oh, here we go. Answers, auto, or decimal. Maybe it's that one. No, it's still giving me it. Math, answer to fraction. Yeah. Yeah. Yeah, it's kind of funny that it's set up to do that for you. It has to be one of the settings. Fraction type, decimal.
Oh, he's using an older calculator. It must have, for words that answers auto and decimal.
It has it's fractions.
Yes, it has auto, decimal, and fraction.
Yeah, so that's what's going on is on the older ones. And I'm not sure if this one's old enough or not.
Press the math, and then like decimal, and then give you the answer.
Yeah, here we go. This one gives you that extra option, fractional approximation. So I think that's what's going on. Yeah, you should be able to. So if you go up here, should probably be able to get an approximation. Gosh, caught me off guard here. How's that one work? Math, and then turn it into a decimal. There you go. Problem solved. Let me give you some homework here for this section. So you go to the math menu, and then after you've got your fraction, you do, the second option, and that'll give you the decimal value off of the fraction. But if you give me your calculator, I can try and change the settings that we need to. For homework, this is section 11.3. Try problems 9 through 23. For problems 27 and 31, I'm going to change things up a little bit. I want you to graph these two functions. So for problem 27, graph y equals 2 to the x minus 2. And for 31, y equals 2 to the x minus 1 plus 2. Additionally, try problems 33, 39, and 41. All right, good luck with that.